Oh dear. Okay. There we go. I was about to say hi to the people, but then we had a visitor. So for those of you listening at home, howdy. God bless your work on the retreat. We have a few new things. Let me just read this off for you in case you can't read it very carefully. Although the iPad's pretty good, you can probably just zoom in. Newton's law of cooling. An item changes temperature at a rate directly proportional to the difference in temperature between the item's temperature and the ambient temperature. And by ambient temperature, I mean basically the surroundings. So if you have an ambiance, that's the surrounding, just environment, so to speak. So just for example, I use the example of take a pie out of the oven at 300 degrees. Where would it cool off faster? In a room of 70 degrees or outside at 30 degrees? Well, it cools off faster outside at 30 degrees because the difference in temperatures between the pie and the surrounding air is bigger. The bigger the difference in temperature, the faster the temperature will change. It also goes the other way. If you have a block of ice and you put it in a room that's 30 degrees, well actually it wouldn't thaw at all, sorry. If you put it in a room of 70 degrees versus a room of 100 degrees, it'll melt quicker in the 100 degree room. But that's because the difference in temperature between the room and the ice is much greater. So the greater the difference, the greater the speed of change of temperature of this thing. Now, review, and this is kind of a first year, second year algebra topic, depending on the book. There are 4 different types of variation. There's direct variation, inverse variation, joint variation, and mixed variation. And in all of these, the constant, I'll tell you what this means in a second, but the constant of variation is the letter lowercase k. So whenever you see a letter k in a variation or proportion problem, you're talking about the constant of variation. What does that mean? I'll tell you in a second. For example, let's assume x and a y, they can be any letters you want. X and y vary directly. Now, what do these 4 types of variation mean? Direct variation basically means as x goes up, y goes up. Or as x goes down, y goes down. They go up or down together. Not necessarily at the same speed, but they both go up or down together. That's called direct variation. One goes up, the other goes up. One goes down, the other goes down. Can anybody guess what inverse variation would be?
Just the opposite, so as x goes up, y goes down.
Right. As x goes up, y goes down, or if x goes down, y goes up. Exactly. They go opposite. Joint variation is when you have 3 or more. For example, as x goes up, A, B, and C all go up. It's kind of like a stronger version of direct variation. It just has more things going up or down in unison. Does that make sense? It's the exact same thing as direct variation. You just have more thingies. There's a leader and a whole bunch of followers. It's kind of hard to tell who's the leader and who's the follower, because if one goes down, all of them go down. They're kind of like sheep. Mixed variation. This has 3 or more. It's kind of what the name implies. They kind of all do their own thing. Each one is going to always do it at once, consistently, but they don't all do it together. Okay. Now assume x and y vary directly. There is a formula for this, and you might want to jot this down. For direct variation, it's x equals k times y. Or y equals k times x. It doesn't much matter, but that is multiplication. The graph of slope-intercept form is very close to being direct variation. It is direct variation without a y-intercept, or with a y-intercept of 0. Inverse variation, well, you tell me. If direct variation means you multiply by the constant, guess what you do in the other way? Yeah, divide. So in this case, x equals, you still have the constant on top, but you divide by the thing that's, in other words, y is going to be going down, so you put it downstairs, so to speak. Or you can do it the other way around, y equals k over x. You note, k is always on top. Because even in these, it's really over 1. So k is never in the denominator. This is not the most exciting stuff to go over. I'll just take 2 more minutes to do this because Newton's law of cooling requires one of these, especially the phrase directly proportional. In other words, you're going to be using direct variation on that. But just for joint variation, it might be this. X equals k times a times b times c. In other words, it's just a bigger version of direct variation. You just multiply all the way out. And in this, for mixed variation, you can do a whole different bunch of things. In this particular thing, KAC over B. Like some things will be on top, some things will be on the bottom. K is always on the top. But the A, B, and C that might be rising up or down depends. If they're on top, they'll go up with X. If they're on the bottom, they'll go down when X goes up. Everybody good? All right, let me just try a quick example. X and Y vary directly. If X is equal to 6, when Y is equal to 10, what is X when Y is equal to 15? So there's one piece of information they gave us. X and Y vary directly. It's a direct variation problem. Which means you're going to use, and it really doesn't matter which one you choose. Either one is fine. This first one's probably easier. Set it up for me. Now again, if it's direct variation, use this. If it's inverse variation, use this. Joint, use this. Mixed, use this. So how would you set this up? Which of the formulas would you use first of all?
Direct.
Yeah, so what's the formula? X equals
KY.
K times Y. Do you notice they gave us starting values of X and Y? Try them. Plug them in and see what happens. So what would I write?
You have 6
6?
equals k times 10.
Yeah. Can you get K by itself?
Divide the 6 by 10.
Yeah. What do you get?
K equals 3 over 5.
Yeah, 6 over 10, which is 3 over 5. This means that we now have a full formula. X equals 3/5 Y. Does that make sense? We've just found the constant of variation. Now, we can finish the problem. What is X when Y is 15? You tell me.
So you set up x equals
Uh,
3/5 times 15.
exactly. Go ahead and do it. Should be relatively friendly.
The 15 and the 5 can cancel
And make
3 times
3.
3.
So what do you get?
9.
9. Done. That's a direct variation problem. Basically, if X is 6 and Y is 10, you notice Y goes from 10 to 15, so X goes from 6 to 9. You notice they didn't go up by the same amount addition-wise. Because you notice Y got 5 bigger X did not get 5 bigger. They didn't go up by addition, they got up by multiplication. So basically it got half again as big. Are you familiar with the phrase? So it's like, if I have 100, then half again as big would be 150. So the original plus half. This is half again as big, so this would be half again as big. So 6 plus half of 6, which would be 9. Okay? And sometimes it's not quite that neat, but you can always do this. Does that make sense, Laura? Okay. These, again, first year algebra, and
Yeah, we did some of this.
Yeah.
you did? Oh, nice, nice. All right, good. Let's try this. Newton's law of cooling. An item changes temperature at a rate directly proportional to the difference in temperature. Now, we need a couple variables. So we need the temperature of the item. I don't want to use I because that's imaginary. I don't know. All right, fine. Just don't tell anybody. Yeah, of course we're pretty good at the temperature of the item is directly proportional to the difference between in temperatures. So let's say Ti is the temperature of the item. And then Ta would be the ambient temperature, which is a fancy way of saying the room temperature. Doesn't have to be a room. If you throw it in a bucket of ice water, then it's the temperature of the water. Whatever you're immersed in. Can somebody tell me how to find the difference in temperature? It's not too hard, but you have to put it together correctly.
Items temp minus ambient.
Yeah, in other words, subtract. Now, there is a bit of a catch. Is the item hotter or colder than the ambient temperature? Did they tell us? They did not tell us anything. It says Newton's law of cooling. It also applies to heating. It just, Newton's law of cooling is the name that stuck. So again, you can throw like a hot something or other in a bucket of ice water, or you can throw a really cold piece of metal into a bucket of boiling water. Either way it'll work. So how do you find the let's just say the difference in temperature. At what temperature does water boil?
212
212 degrees
degrees.
Fahrenheit. Correct. At what temperature does water freeze? 32 degrees Fahrenheit. If I threw an ice cube into boiling water, what's the difference in temperature? 212 minus 32. Correct, whatever that is. Like 180, I think. Yeah. Now, what's the difference in temperature with a bucket of ice and a spoonful of boiling water? Same thing. Wouldn't it be negative 180? No. Why not? When I ask for the difference, I'm always looking for a positive value. Guess what does that in math?
Absolute.
Absolute value. Ding, 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 ding. So in other words, the difference in temperature is going to look like this. The absolute value of TA minus TI. That's the difference in temperature. We need absolute values just to make sure it's positive. So, they're claiming that, man, I filled up the board. Maybe I can sneak this in down here. They're claiming that the temperature of the item is directly proportional to that difference. Now let me see over here. If x and y are directly proportional, then you have x equals ky. If you have a is directly proportional to b, then a is equal to kb. You can use any letters you want. They're saying the item's temperature is directly proportional to this. Give me a formula. What's the item's temperature? What are we using?
TI.
TI is equal to what? If it's direct that's where Newton's law of cooling comes from. Now, does everybody have these four proportions? Okay. And I'll post the video in case you need to grab them again. My question is, they're going to start asking questions about how fast something cools. Ooh, my goodness. I've got something that's not quite.
It says good.
Actually, hang on a second. Oh, I missed something. There's a problem with doing it first off. Hang on a second. The rate is proportional to the difference. So, that's right. The one teeny thing I missed. What's another word for rate? Like the rate at which I do something. Close. Speed. Or velocity, if you want. Excuse me. So the rate at which I do something, it's called the rate of change. Think back to like chapter 2. In calculus, what do we call a rate of change?
Acceleration.
That's the rate of change of the rate of change.
Okay.
You're close. How do you get it? Oh, that's an good question. How do you get acceleration? Start from the beginning. Let's say you have a position function. I'm standing at position 0. I'm walking forward such that my position is 5t, where t is the number of seconds. How do I get my velocity?
T equals v
And not this problem. This is chapter 2. It's something we've been doing a lot.
Oh, can you do the derivative?
Aha! The derivative is the rate of change.
Oh, yeah.
In other words, the rate of this thing is directly proportional to the difference in temperatures. So let's do this. The temperature of the item, let me just put it over here. The temperature of the item is going to be some number. Does it make sense that the item's temperature is going to start changing? Okay, I'm going to write it like this. This is going to look really psychotic, where t is time. I don't know what the formula is yet, but I do know that as time goes on, the temperature changes. It might be, just as an example, T1 might be 70 minus 3t, where t is the number of minutes, something, or hours, or whatever. Actually, probably hours. Things don't pull up that fast unless it's just thrown into a freezer. So does that kind of make sense? What is the temperature of the item when you first start the experiment? When time's 0?
Oh, so it'd just be 70 minutes.
70.
Or 70,
Yeah, 70 degrees or whatever. What about after 1 hour?
67?
67. What about 2 hours?
64.
Yeah, see how that works? So it's some sort of formula, Ti of t, is that. Does that make sense? Now, the difference in temperature is directly proportional not to the temperature of the item, but to the rate of change of the item, which is what?
The derivative.
The derivative.
Mm.
Right. So I'm going to write this as the derivative over time, over derivative. In other words, with respect to time. The derivative of the temperature over the derivative with respect to time. It's kind of like dy over dx. Does that make sense? Now, my question give you a setup. Is everybody okay with this? Everybody?
Yeah.
Okay. Here's a typical type of problem. This was actually, when I was getting certified to teach AP Calc, which by the way, I'm not a big fan of AP Calc, but there was a week-long seminar, I don't know if I told you about this or not already, but the professor was an absolute math god. It was actually pretty amazing. Teaching AP Calc, but the training was totally a blast. There are like 45 math teachers that all have the same sort of weird sense of humor. It was awesome. They were also doing these sort of math and physics jokes. I'll tell you one in a second, but just to give you the idea, I'm going to steal this from his test. He said, you come into the class in the morning to find your professor, me, dead on his desk, on my desk. Fortunately, you brought along a thermometer and you know Newton's law of cooling. So they take a temperature of the body, make a note of it, and then wait an hour, and then take the temperature again. And they say the body will have cooled a little bit. Given how much the body is cooled, and given that a typical body is 98.6, more or less, degrees when he was still alive, and when the instant he died, you can extrapolate the time of death. Because you can say it would take however many hours for the body to cool that many degrees. So you can go back in time and say, wow, he must have died 71 hours ago. Does that make sense? That's actually one of the uses for Newton's law of cooling. It's kind of a grim one, but let's try that. Let's assume, God forbid, you come in to find your math teacher sprawled on a table, dead, with a knife in my back.
Oh my goodness.
So heaven forbid, but
That first thing we'll do is take your temperature.
yeah, first thing I'll do is take the temperature of the body. Hopefully you'll have one of those scanny things where you kind of have to
Yeah.
So I'll say no more.
COVID test.
Well,
Yeah, come on.
yeah, I'll be beyond COVID tests at this point. So let's just say the original temperature was 98.6 degrees Fahrenheit. And let's just assume, now you will also be able to take the temperature of the room if you have a thermometer. So let's just say the room temperature is, just to make it easy, 70. I think it's usually colder than that, except in winter lunch, it's like 90. But I digress. And does it make sense that if, when I die, God forbid, and my body stops generating heat, it's going to start cooling off. Eventually, it'll get closer and closer and closer to 70. It'll never actually reach 70. I mean, what's that called? Get closer and closer to something you never touch? The graph? Starts the name.
Gravity? Wait.
What?
Asymptote.
It's an asymptote, correct. So it's going to be a horizontal asymptote at 70. So the temperature is going to go down, flatten out. It'll be like 71.5, 70.3, 70.1, 70.04. If you go forever and ever and ever. Finally, it'll get so close that our temperature readers can't tell the difference. But it'll never actually get to 70. But it will be cooling down. If the room is colder, the temperature will drop faster. So let's assume for the sake of argument that you come in and horror of horrors, I'm there dead with this, Julius Caesar style with a bunch of knives in my back. I made the wrong mathematicians angry or something. The mathematical mafia took me out. So, you come in, and let's just say you find right now, at T equals 0, the body temperature is 82 degrees. And then normally you have to wait a little bit longer. Because if you wait 1 hour, it might only change a teeny bit of so the longer you wait, the more it's going to change. So let's just say we wait 4 hours. And then the body temperature is now 79.
So you want the T=0, that's like when you come in, it's not when the body.
Correct,
starts
correct.
moving.
So the time when I actually died is gonna be t=negative something, it's gonna be back in time. Right. So at the very beginning, because there's no way to tell you, otherwise you'd have to give me a number of how many hours I died, and we don't know that yet.
Okay.
So this is when we first start the experiment, so to speak. Well, when you start the experiment, because I'll be hopefully in the kingdom. Please God, or in purgatory, whatever. But please God. I'm not waving at you from perdition. Sorry, I guess I shot one too many guys. Moving on. So the body temperature dropped 3 degrees, right? Now, can somebody set me up here? It says the change in temperature is directly proportional to the difference in temperature. Now, set me up for, we do not know the speed at which it changed, but we do know there's one sample. So t is equal to 4. There's one other thing I should probably tell you. Chapter 3, maybe? There are two different types of rate of change. There's average rate of change. I wasn't planning to take this long on this. An instantaneous rate of change. And I will tell you on a graph, we've heard of this even in first year algebra. The average rate of change is called slope. But instantaneous rate of change is also called slope. There are two different types of slopes, I remember? Way back at the beginning of the year. First year algebra, slope needs 2 points. Remember what that's called? What kind of slope uses 2 points? Like if you have a curve and it punches through twice. Remember what that's called?
Oh,
If it only hits once, it's called a what?
tangent.
The tangent slope.
Isn't that secant?
Yes, secant slope. If it punches through a curve twice, it's a secant slope. That's the average rate of change. So it's a secant slope. And then the instantaneous rate of change, like what is the slope at that very instant, is the tangent slope. That uses 1 point. Well, really, 2 points that are insanely close together. Okay. So the average rate of change is delta y over delta x. And the instantaneous rate of change is dy over dx. Does that make sense? Right. Now I'm looking at the clock. I wanted to actually go over a few of the problems on the test for your sake. You know. So I think I'm going to put a bookmarker in this. And so for those of you watching at home later, consider this a teaser of what's coming up tomorrow. No, not tomorrow, because tomorrow is the in-class retake. Thursday, we'll continue Newton's Law of Cooling and the Mr. Cosper murder mystery. And I'm going to, oh no, I was going to take a picture of this, but I didn't have the video. I am Mr. Low Tech today. So I think that we're just going to put a bookmarker on that. And let me go get the answer key for you there, Leo. And yeah, I'm still kind of figuring out what the heck to do today because half the class is gone. And I was not remembering that, so I'll be right back.
May I start?
Absolutely. Yeah, and I can probably just hit the video off. So this is probably totally exciting for everybody. Like people going to the bathroom, getting copies, etc. To be continued. See y'all later.